Hello everyone, welcome to another Python video. We're going to be going through a solution for the question 14 on Project Euler, the longest Collatz sequence. And this is a revisit because this solution is a lot more elegant with dictionaries. So there is a iterative sequence, and we can define it and create the sequence by following this rule. If that current number that we're looking at is even, we divide it by 2, and then if it's odd, we multiply by 3, then add 1. And if we continuously do this over and over again, we're hoping that it finishes at 1. So by using this rule, if we had 13, 13 would generate 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. So it can be seen that the sequence starting at 13 and finishing at 1 has 10 terms. So it hasn't been proven yet that every single number in the universe will end up at 1, but we're going to be analyzing all the numbers from 1 to a million, and we're going to see which number under a million will produce the longest chain. Right, 13 generated 10. We're going to see which number generates the longest chain of where it has the most many terms under 1 million. And this is going to be our solution. So starting off, we have a very simple function that helps us to generate the next value. By analyzing this argument integer that we've been given, if it's even, we divide it by 2 and return that next number. If it's odd, we're going to multiply by 3 and then add 1 to it, making sure that we're following the Collatz sequence rule. Okay. Now, this is where our code becomes a little more complex. Okay. So starting off, we wrote a function that has a starting number. We're going to be starting at this number to generate a Collatz sequence. And then we're also going to be asking for a dictionary. We're going to double check if this number or the numbers that we generate in our sequence have been calculated before or not, so that we can speed up our calculations easy. So right away, if at any time we're given a value that we've already calculated before, we're just going to return the length because we already calculated. We don't need to do any of our fancy calculations right here. If that number is something or a number that we've never calculated, what we're going to do is just initialize a very short list with that single value within our list as our starting point. And our size is 1. We haven't calculated it yet, but we know that we at least start off with 1 value. And then we're going to be in this while loop. We're going to say while our last value is not 1, and that we have never analyzed the very last number before this last number before. So as long as that is not inside our table, right? Because if it's inside our dictionary that we've been given, that means that we have seen this table before, okay? So right away, we're going to take that last value in our sequence and we're going to generate the next number from it. So we're going to say next value, grab the next value by starting from and analyzing this list. So if our list is 13 at the moment, it's going to grab 40 because 13 is odd. It's going to go into this function here. Take 13 multiply by 3 gets 39 and add 1, we're going to get 40. So our new number is 40. And at any point, as we keep on generating these new numbers in our while loop, and if we have ever seen it, well, then we know that, well, we can take our current size, which is going to be updating right here. We're going to be taking that current size, well, and we have seen it. We know the answer, the length, the number of sequences that takes to get to 1. So we're just going to add it onto size and we can break out of the loop very easily. Otherwise, we're going to say that, well, we're going to add that new number. We have never seen it before, so I'm going to add it onto the sequence and increase our size by 1 because our sequence, our series is growing, our Collatz sequence is growing, right? So we're going to be increasing that as we go. And then after that is over, as either we grew this or we were able to land a number at a point where we have calculated their sequence length before, so we were out of the while loop, what we're going to do is just quickly check that all these numbers have their appropriate sizes, okay? Because these are some of these numbers that we have populated in our sequence list are numbers that we have never seen within our table. Therefore, we're going to say that in our dictionary, we're going to take that value inside our sequence as a key, and we're going to assign it with size minus I. So we're going to start off with the very first number that we have started from. So in our example is 13. We have calculated the size of 13, having 10 terms in their sequence. So we're going to say, well, size should be 10. I starts at 0 because our range starts at 0. We're going to assign 13 with a size of 10. Okay, and then 40 is going to be assigned with a size of 9. So let's see that in action. I have separated my output for my program into two parts. Okay, it's going to say that 13 has 10 many terms. And as we calculated 13, we can say that, well, 13 has 10, and after 13, it generated 40. So 40 is going to have 9 terms. And this is where that magic is coming from. As I increases, I'm able to subtract values from my size to get the proper length of all these sequences. 20 is going to have 8, 10 is going to have 7, 5 is going to have 6, 16 is going to have 5, 8 is going to have 4, and 4 is going to have 3 terms. Okay, and after 4 divided by 2 gets us 2, so 2 has 2 terms, and 1 is going to have 1 term. So to make my life easier, what I've done is we have this. Okay, we have a memory dictionary. This is going to be the dictionary that remembers all the solutions that we will be solving. And I said that just for our very simple numbers like 1 and 2, we have their answer and the number of terms they have in their sequence. So the key is going to be the starting value of the sequence and the length of the sequence for the starting value. So in our first output here, what I've done is just calculated what the sequence would be for number 13 and how many terms it would have. So we get that output that 13 has 10 many terms. And then I want to show you what our dictionary has by telling you our key value pairs as our memory. As we continuously generated new numbers, right, we were able to also calculate their size for it. Then what we're going to do is now reset my memory variable and look at all the numbers from 3 to 1,000,000. And then we're going to get their current length and look at get the current length by running the sequence making function by telling it to start at this value and use this memory table. Now the cool thing about this algorithm is the following. Our function is a function that is mutating an outer variable that exists. Okay, we're going to pass on an argument, which is a dictionary, which we called memory in line 58. And anytime this function is called and anytime we do an update, since dictionaries are mutable data types, we're actually mutating that outer dictionary that we have passed on and giving it new values. So this function ends up having a side effect on our memory dictionary so that we get to continually track new values that we are encountering just because we started at this starting number. For example, if we started at 13, we were able to calculate the solution for 40, 20, 10, 5, 16, 8, and 4. Therefore, I will be able to dodge and not do calculations for those numbers because if I run into, let's say, 40, we would have already calculated it. So if 40 would be inside our table, therefore I can just return the result as 40 has 9 terms. Okay. Then what we do is that once we have analyzed every number from 3 to 1,000,000, I can just quickly generate all the possible keys from 1 to 1,000,000 and just check that if the length at that key location is greater than our longest length variable, which we've been tracking outside, right? We'll just continuously update those two variables as we go over and over and over and over and over again so that we can output that the longest sequence had 525 terms and it was generated by the number 837,799. So this is a really nice way to learn and be introduced to the world of dynamic programming. Dynamic programming is something that's not like shocking, but rather it's like use of using the concept of remembering the solutions that's been created before so that you don't have to redo those calculations over again and you start to build upon the solution from previous solutions made. And so this was a really nice introduction to a concept called dynamic programming. And as always, thank you for watching and stay classy.